the Hangout on air is now live. Thank you all for joining us. Either you're here physically or you're joining online. We have a fantastic seminar speaker this evening. This is Dr. Meg Rosenburg. She has her BS in Planetary Science and Physics with a minor in Literature from the Massachusetts Institute of Technology, and a master's degree and a PhD with a minor in History and Philosophy of Science from Caltech. Dr. Rosenburg has got an extensive CV, a lot of very interesting activities and awards, but what's highlighted here, what's really interesting, there's a lot of outreach and science communication activities. And so her CV has got a very fantastic paragraph here that I want to read. As a scientist, historian of science, and communicator, I'm committed to active engagement with the public and effective communication through storytelling to increase science literacy. I believe that exploring new media to connect historians and scientists with broader audiences is crucial to expanding public understanding of science and engineering in our modern world. It's almost as if we cloned her to do this seminar for ourselves right here. So, fantastic. I want to be sure to say that this seminar series is sponsored by our University of Central Arkansas Foundation, and the title for the seminar this evening is Craters in Context, Science and History of Impact. So take it away, Dr. Rosenburg.
All right, thanks very much for that introduction. Thanks for reading my CV. I do very much believe that entire paragraph, and I guess I'm going to try to pull up my presentation and just give you a little bit of background on where I'm coming from, or how I came to study craters and the moon and be involved in the science communication things that I'm involved in now. So, screen share. Okay. Okay. And please let me know whenever, if there's a question that comes up, by all means interrupt me. I'd rather answer it while we're going than necessarily to do them all at the end. And also, if there's any time that you can't hear me, or if the picture goes away or anything like that, just please let me know. So anyway, my name is Meg Rosenburg. I did graduate from Caltech last year, and my PhD is in planetary science with additional specialization in the history and philosophy of science. I kind of organized this slide. It's not very organized, but it's kind of organized around the principles of my life right now, which are planetary science, history of science, and science communication. And those are the three things that I spend most of my time thinking about. The planetary science side we'll talk about a bunch. The history of science side I hope that we'll get to talk about a little bit. The science communication side really kind of ambushed me when I was a graduate student. I didn't really know that that there were opportunities for people to communicate science as a primary way of relating to science. As an undergrad, I loved science, and I loved understanding things, and that is what compelled me to go to graduate school for planetary science. But in the middle, it kind of I became aware of these sort of science-adjacent fields where you can love science just as much, but you're participating in it in a slightly different way. So I came at science communication via the PhD comics movie. I was involved in that when it came to Caltech, and the webcomic creator Jorge Cham wanted to film a live-action film based on his comic strip about grad school, and I got involved in that, and I ended up producing the movie, and that sort of opened a whole world to me of what's out there in science communication, and I worked with PhD Comics on several videos after that, and currently I'm a freelance science communicator, and also I'm writing my history of science research. So that's really kind of come around full circle for me. I do some podcasts for the Physics Central podcast. I do some outreach activities and videos for planetary missions at JPL, which is really close, including the Orbiting Carbon Observatory. And I do some writing here and there on my own blog, which is trueanomalies.com, and that's also my Twitter handle. Anytime you actually want to ask a question about cratering or whatever, you can always contact me that way. And I also have written a few pieces with Trailblazers, which is a website that's devoted to sort of identifying and writing about women in the history of the trowel-wielding sciences, archaeology, paleontology, and geology. so they can be often overlooked. So anyway, that's kind of where I'm coming from. I'm going to talk today mostly about crater science, but possibly also, I hope, a little bit about the history of crater interpretation and why anyone would bother learning about it. So yeah, let's just get started then. All right, so I'll give you a sense of where we're going. We're going to spend a little bit of time. This is kind of a roadmap mostly for me to try to stay on track. When I was putting this presentation together, I realized that there are a lot of different aspects of cratering that you could cover, and in fact, like when I was pulling slides and figures from all of the presentations from my own graduate classes and other graduate classes, I realized, you know, in graduate school you spend 2 or 3 lectures just on the different aspects of cratering, and there's whole fields that have you know, have to do with specific aspects. So I'm going to try to call those out when we come across them, and hopefully not gloss over too much. But if you are interested in a particular thing and you would like more resources to go in a particular direction with that, by all means, just ask, and I'd be happy to point you towards either, you know, reading material, or if I happen to know research groups that work in that area, that kind of thing, I'd be happy to point you in that direction. So we're going to talk about what is an impact crater to begin with, and why do we care, and then a little bit about the impact process itself, the mechanics of impact, and the kinds of crater types that are created that way. And then we'll get a little bit more towards what my own research focuses on, which is cratered landscapes and the evolution of crater terrains and how you can look at those in a statistical sense and what kind of information you can get from that. And then I would like to spend some time talking about some crater history, and then just in general, cratering history is sort of one case of what is really a general principle in planetary science. We use analogies a lot in planetary science, just like we do in geology, in astronomy, and I think this is it's a good example to start thinking about how we actually do science, and what are the ways in which we actually are making knowledge this way. So, and then hopefully, by all means, interrupt me with questions. Okay, so what is an impact crater? I know that you just watched my short video, which was really nice for you to provide that for people to watch. But an impact crater, basically, it's a hole in the ground. But it's a very special hole because it's the product of a hypervelocity impact. And hypervelocity is kind of a buzzword a little bit, but generally it means something that's traveling at a few kilometers per second. So I think Wikipedia says more than 3,000 meters per second. So that's actually faster than anything that I could think of that I experience in my daily life. I try to think, you know, an airplane doesn't come close. Even a bullet doesn't come close. Some go faster than 750 meters per second, but not that much faster, nothing approaching a few kilometers a second. But then, you know, I thought about it some more, and you can kind of think about the amount of time that the Earth takes to travel around the sun in 1 year. And, you know, it doesn't exactly travel at this speed all the time because it's a little bit elliptical, and it speeds up and it slows down, and it's perturbed by all these other things, of course. But, you know, and then back of the envelope calculation, the Earth is traveling at 30 kilometers per second all the time. So it's not that unusual after all, and that gives you a sense of the speeds at which things are whizzing around the solar system all the time. And collision, when you think of it that way, is not an unlikely outcome of all of these kinds of masses. So, sorry, get my thoughts together. Why do we care about craters to begin with? So just first of all, I have to mention, you know, impact cratering is the dominant landform on many of the surfaces that we see in the solar system. So just for that reason alone, we can't begin to understand those places in the solar system, and maybe someday outside our solar system, maybe. We can't begin to understand that unless we have a very good understanding of impact craters and how they change their environment, how they modify the landscape. So beyond that, impact is a very important delivery mechanism between bodies in the solar system, and when people talk about this, they mostly are talking about water, for example. How did the Earth get its water? Was it delivered by comets? Was it delivered by asteroids? You know, there are places on the moon that are cold enough and never see sunlight, and we think that there are potentially volatiles trapped there that, you know, were delivered in some impact some time ago, made their way to the polar regions where it's very cold, and just have been trapped there ever since. And not just volatiles, we actually have meteorites from other bodies in the solar system as well. So an impact on Mars knocked off a chunk of Mars, and it tumbled through the solar system, and eventually it hit Earth, and somebody picked it up, and somebody analyzed its chemistry and looked at the gases that were trapped in little bubbles in the meteorite, and realized that they matched the composition of the atmosphere in Mars, and that they had to be from Mars. And that's an important source of information, especially geochemical information, about the kinds of materials that are making up other bodies in the solar system. And we also have meteorites from the moon. We know that, and we also have samples from the moon, but those weren't delivered in an impact. We're going to talk a little bit about relative age dating of cratered surfaces. So I won't dwell on that too much now. But then the size distribution of craters can also tell us about the impactor populations that are responsible for producing crater terrains to begin with. And that's important because there are people, and this is one of those places where this is an entire field of study all by itself, but people who model solar system formation with computer models, dynamic models, and this is an important constraint for those models because it's telling you if you could match the distribution of craters to a particular population of impactors out there in the solar system, like the asteroid belt or like the Kuiper belt, if the size distributions line up perfectly and you say, well, that population created these holes in the ground, then that's something that we would be able to feed into the model and say, well, we have to recreate this situation somehow. How do we do that? And then craters, just geologically, they can give us clues to composition, and they can actually expose deeper materials that we would otherwise never be able to access. So they're kind of like probes also. They can bring up material to the surface that would normally belong in layers that are far below the surface. They also can affect planetary orbits and rotation. You know, a major theory for how the moon was formed, although there are lots of different versions of this theory, is that it formed in a giant impact. So, for example, the moon might not even be here if it wasn't for this impact. And there have been large impact theories to explain lots of other things in the solar system, to explain why Mercury's crust is so thin, to explain why Venus's rotation is so slow. Uranus is tipped over on its axis by 90 degrees, and that's pretty weird. You know, it's not to say that any of these are necessarily what's actually going on, but we think that that impacts, especially large impacts sort of near the end of the accretion phase in solar system formation, are really responsible for some of the major characteristics of some of our neighbors. Okay, and then finally, of course, we care about craters because we suspect, or we expect, that they've had an influence on the evolution and persistence of life on Earth and maybe possibly elsewhere. And of course, we think about the extinction of the dinosaurs, for example, as one, classic example of that. But there's also this other way that they can affect life, and this is another area of study. It's not my area of study, so I can't say too much about it, but I know there are people researching the ways in which craters may be able to create environments that can foster life, because they're an important source of heat. So they can generate, geothermal systems around them that persist for some amount of time, and that could actually be an environment where life could be created or evolved. So that's generally all these different reasons why we actually care enough about craters to spend any time talking about them. So let's take a little tour of craters in the solar system. We have our nearest neighbors. There's also Venus on here, but it's a little bit different. Venus was completely resurfaced about 1 billion years ago, and it has very few craters compared to the other terrestrial surfaces. You can see Mercury, for example, is very heavily cratered terrain. Mars also covered in craters a little bit more in some places than other places. Mars also has an atmosphere, so it has some competing, geomorphological processes going on. It's got impact cratering, but also there's wind. There was flowing water at some times in some places, at least. And then we have Vesta, which is the second most massive asteroid in the asteroid belt, and the Dawn mission just put together this beautiful image mosaic of Vesta, and now it's approaching Ceres, so that's really exciting. And you can see that in the inner solar system here, we have our terrestrial planetary bodies covered in craters. That's important for them. And then we get to the outer planet satellites. So these are the moons of Jupiter, of Saturn, of Uranus, Neptune. And in a lot of cases, the materials here are not quite the same as they are on Mercury or in the asteroid belt. The ratios of the materials are not exactly the same. And in a lot of cases, this is actually more icy than rocky. But it's so cold that the ice behaves like a rock at those temperatures. And so the kinds of things that we can learn using craters in the inner solar system, we can absolutely apply to craters in the outer solar system. And the differences and changes in the way that craters behave, the shape that you get from different things, can tell us about the material properties of those bodies. And we have craters on Earth. I think there are about 170 known or identified terrestrial impact structures. They don't look the same as they do on other planets, most of them, and that's because there's a lot going on Earth. For one thing, we don't have as many because we constantly erase them. The ocean floor at its very oldest is only about 200 million years old, which is not that old, and it's constantly being subducted under the continents, so we're always sort of rejuvenating ourselves. And so that's why all these dots are showing up on the oldest parts of continents. So Canada has a lot, Australia has a lot, because those are the places where you can find things that are old and accumulate enough numbers to see them like that. So you can kind of also see in these pictures that you have to kind of look for different kinds of markers of craters on Earth. There are a lot of geological markers and geophysical markers, signatures of impact that you have to look for in order to identify them, because they're being weathered away, there's tectonic deformation. There's just, Earth is a very dynamic place compared to a lot of other places in our vicinity that have a lot of craters. Okay, and then of course we have the moon. Let's talk over this. So this is the parting shots from the GRAIL mission. That's the Gravity Recovery and Interior Laboratory. That was launched in 2011 and crashed in 2012 on purpose. This is the last bits of footage from the MoonCam, which was actually an outreach project. It was a camera, 2 cameras, one on each spacecraft. There's a pair of spacecrafts. They fly in tandem with each other, and they can keep track of each other very closely. And then little perturbations, little accelerations due to changes in gravity as they're flying over the surface will be registered, and they can map the gravity fields of something very accurately. There's a similar mission around Earth that's been going on for years and is really cool. It's called GRACE. Same principle, but Earth even has lots of bodies of water moving around and stuff like that, so you can see the time-dependent gravity field, and that's really neat. But anyway, I'm just showing this video because it's the last, right before they crashed, they took this video, and you can just see the scale of craters, the how small they get, to the extent that you can see in this video, and then how big they get, and you can see all the different states of degradation that they're in. So the moon, it turns out, is kind of a natural laboratory to study impact processes because it's just such a dominant process on the surface. Okay, so we took our little tour. So let's talk a little bit about impact physics, what's going on in the actual process. Traditionally, people divide this into 3 different stages, which kind of makes it easier to think about, but it doesn't really. There's no breaks in the process. Everything is continuous. And I'll just tell you the 3 phases are first contact and compression, then excavation, and then modification. So the first phase is the briefest, and what happens is you've got this projectile. It's coming in, remember, at a few kilometers a second. It makes contact with the target, and it transfers a lot of its energy to the target rocks. And that initiates shock waves in both the target and the material and the projectile, and it accelerates the material in the target, it decelerates the projectile, and again, it's coming in at a few kilometers a second, and the speed of sound in rock is also a few kilometers a second. So that's, you can see where the shockwave part comes from, because there's actually no time to communicate this wave. It kind of overtakes the material. So anyway, this shockwave is propagating backward in the projectile, and at some point it hits the other side and it breaks, and then that initiates a second wave, which is a rarefaction wave, a release wave, that propagates back towards the center, or towards the target body, and then both of those sort of are propagating through the target material. There's a shock wave followed by this release wave. Okay, yeah, so this shock wave is expanding. It pretty much takes on the shape of a hemisphere, and the target rocks are kind of overtaken by this shock wave. They're very quickly compressed, and then they're released again very rapidly. And what that does at the peak shock pressures is it can result in melting and even vaporization of the target material and projectile material. And then as the shock pressure attenuates with distance away from the impact site, you get other kinds of markers of impact. For example, you get high pressure phases of minerals like quartz, and you also get these features called shatter cones, which are really fun, and I should have pulled up a picture of one, but they're like points in the, they're like perturbations in the layers, and the shock waves sort of hit them, and they create this little structure that has these striations that point to, so it makes this kind of cone that points to the direction of the impact site. And if you find one of those, and it's in, in situ and everything, like that's a really important way that people have identified impact features on the Earth, when other more obvious markers have been erased. So crater excavation kind of proceeds then along these, I should say, yeah, so the shock process is thermodynamically irreversible. So it actually leaves a residual velocity after it passes through, and that velocity field is what excavates the crater. So those follow these sort of downward then outward flow paths, and you form what's called a transient cavity. So this is another way of illustrating the same thing. And you can see, so the transient cavity is sort of a typical bowl shape like you'd expect, and then you get this ejecta curtain. And what's going on in the ejecta curtain, it's this process called ballistic sedimentation, where ejecta is being thrown out on ballistic trajectories in this sheet, and that ejecta curtain is propagating outward with time. And the bigger, heavier particles don't make it as far as the smaller, lighter particles, and they can be going very fast. And then also there's sort of a differential mixing of the ejected material with the local material that it lands on as you go further and further out. So the smaller particles that are being tossed out at really high speeds are landing farther away, and they're also mixing more with the local material. That's kind of what is being illustrated by these insets here. And I think you can see the ejecta curtain sort of moving outward, and this is sort of the classic impact experiment, or what you would see in a simulation of an impact, where you can see it propagating further and further, and that's the crater being excavated there. Okay, and then there's a couple others there. But okay, so, and then the very last, the slowest bit of ejected doesn't really get thrown out, but it kind of like flops over. And what you end up with is you get this sort of uplift around the rims. The layers are tilted upward compared to the original horizontal layers, if there are horizontal layers in the target. This picture is based on Meteor Crater, and those are the originally horizontal layers of sandstone, then limestone, then another really thin red sandstone. And then you kind of get this, especially in that case, you can see it really clearly, you get this inverted stratigraphy with the fold hinge. So that's called the overturned flap, and you can see it really clearly when you're there. There's not that many places around Meteor Crater anymore that you can actually see the fold hinge, but there are a couple, and I've seen it, and it's really cool. You can see the rock layers actually bend upwards, and you can see the the planes of the bed, so they sort of tell you what the direction, the originally horizontal direction was. You can see it's completely folded over. Okay, and the final stage is modification. So you've made your transient cavity, but that's not a very stable shape, so there's always some sort of collapse afterwards. And that collapse kind of takes place in different ways depending on how big your impact is. So for its kind of small impacts, they make what we call simple craters, where they kind of look just like the transient cavity, but there is some modification that happens. So material from the walls collapses to the middle and it forms this breccia lens, where a breccia is a kind of rock that's made up of fragments of lots of other rocks, and an impact breccia is another marker. You can tell that an impact happened in this place. It's just a very characteristic because it's breaking everything up, and then it creates this characteristic lens in the bottom of the crater. And then all around, underneath the crater, the rock is fractured for quite a depth also. If you move to a slightly bigger impact, the collapse happens in a much more complicated way. That's why we call them complex craters, I guess. So we have simple craters and complex craters. And complex craters, there's actually some rebound from the middle, so you get this giant transient cavity that's not very stable. You get uplift in the center that can form peaks, central peaks, peak rings, a lot of different kinds of features. And in addition to that, the walls slump down in this characteristic way, forming these terraces, and you can also get big melt sheets along the flat floor. So the complex crater shape in the end is much shallower than the simple crater shape because it's been extensively collapsing. So you might wonder, why does this happen? Why are there different outcomes if you have a big crater or a little crater? And the way we think about it typically is that we say, well, they're in two different regimes. There's the strength regime and there's the gravity regime. And in the strength regime, if your crater is small enough, then that cavity can be supported by the strength of the target material by itself. It doesn't feel gravity. And in that case, we can kind of think of a very simple energy scaling, and you can say, well, the impactor's coming in with a certain amount of energy. What is the volume of material that I can break with that energy? And that'll maybe tell me about the final size of the crater that I would expect. So here's a very simple energy scaling where we have, okay, so the impactor energy then is proportional to the yield strength of the rock and proportional to the cube of the crater diameter, the volume, the final volume. And we can sort of think through the same process for the complex crater case, where we're now in the gravity regime, where larger craters can't be supported by the target material anymore. They collapse in a different way. And now it's not so much, the size of the crater isn't so much determined by how much can I break, it's determined by how much can I excavate, how much can I physically lift out of the crater. And so you can think about it, again, a very, very simple scaling. The impactor energy proportional to the mass times the surface gravity times the height that you have to lift it, which ends up producing this relation where it's proportional to d to the fourth. And so if you wanted to say, well, where's the transition, then you could set those equal, and you would find that the transition diameter, the going from simple craters to complex craters, scales inversely with surface gravity, and that's in fact exactly what we observe. We've measured the shapes and sizes of craters on a lot of different, places: the Moon, Mars, Mercury, all those icy satellites as well, and the transition between the two forms does scale as 1/g. So that's pretty fun. And you can see it also for the case of lunar craters. This transition happens near about 15 kilometers. And you can see it really clearly as a break in the depth to diameter scaling. So that's a typical shape parameter for craters. You can see this is a log-log plot, but if you plot the depth against the diameter, you get a straight line because it's a power law. And it's got a slope of about a fifth. So simple craters are about a fifth of a diameter deep. And then there's a very clear transition when you get to complex craters, and they're much shallower for their size, and they go down to about a tenth. Okay, and as you get bigger and bigger impacts, you start to get into the impact basin range. For example, this is Schrodinger Basin, and it's a peak ring basin, where instead of just a central peak, you actually get a ring. And then there's also Oriental Basin, which is a multi-ring basin, so you can see many concentric rings. And the scaling of the transition is not as straightforward as it was for simple to complex craters, mostly because these are tectonic features, and a lot of the outcome of what you're going to get after an impact of this size depends on the particular structure of the target material before. So it's actually still kind of a mystery how multi-ring basins work in detail, and there's different kinds of those too. But if you wanted to know more about that, that's a whole other that's a whole area of study all by itself. So anyway, I thought maybe I would take the opportunity to show you something really cool, I think. Hi. Yeah, so this is a website that's run by ASU, and it is based on data from the Lunar Reconnaissance Orbiter camera. So the Lunar Reconnaissance Orbiter is orbiting the moon right now. It's got excellent set of cameras, a wide-angle camera, a narrow-angle camera, and you can like pan around the surface of the moon and go look at things, which I don't know if you think that's fun, but I think it's fun. So for example, there's lots of layers. This is Copernicus crater, which is a very prominent crater on the near side of the moon. It's got these very dramatic rays, and you can see some of those features that I was talking about, complex craters. It's got a central peak. It's kind of a complex of central peaks, and then it's got this, you know, very terraced rims, and you can, I think if you zoomed in really far and you were a better geologist than I am, you'd be able to distinguish the melt pools and the melt sheet that's in the relatively flat floor otherwise. And then if you just sort of look around it a little bit, you can see that the smaller craters don't quite look like that. Those are simple craters. And then we could do something fun, like go all the way over to Oriental Basin or something. Anyway, and there's lots of different layers. There's topography they actually have a whole topographic map using the camera, which you can do with stereo imagery, which is pretty cool. And they have a whole base map, I think at 100 meters per pixel. Yeah, it's just a fun thing to kind of poke around with. Okay, here we are. Sorry, it could take a while to learn. Okay, that's Oriental Basin. You can see it's also, you know, it's got some Maria deposits in the middle. That's the dark stuff. And it's also got a lot of craters on top of it. And that's, well, I guess I'm jumping the gun, but that's how you can tell how old things are by looking at, you know, the crater distribution that has had time to accumulate on top of them. So you can do very detailed crater counts just around Oriental Basin and get a sense for how old this particular structure is, and then how does that fit into the whole lunar history. So that was fun. I'll go back to my presentation. Are there any questions? Am I speeding through in a ridiculous fashion?
No, this is great. We definitely enjoyed seeing the two energy regimes, and then how the transition where you look at both of those equated together really follows along with that plot that you showed. That was really cool.
Yeah, I like that. I think that was a homework problem in my first week or something in grad school.
Excellent homework problem. I've seen like undergraduate labs and sort of also at the high school level where you drop like ball bearings and
yeah,
from different heights into like sand or sugar, and you kind of can do a similar sort of graph. But I wanted to be sure at some point to ask you, were those built on some solid foundation, or are they a little too hokey for an introductory type lab?
You mean the dropping projectiles?
Yeah, and measuring the diameter of the cavity in the sand.
So it's a little bit, it's a really good activity to do, but you're not getting the same physics at all. So you have to go in knowing that. I mean, you can do some things like the faster I drop it, the bigger the cavity. You can kind of get to some sort of energy scaling that way, but it's a different energy regime. So yeah, it's kind of it's a neat activity. I did it once with little tiny kids, which was kind of a mistake because I used powdered sugar and they just wanted to eat the sugar. But but it was all right.
That's good to know.
Yep. Okay, let me find my presentation again. Okay. All right, so I just want to take that brief break and look at the actual moon for a second. Is this working? No. Wait. Do you see the presentation?
Yes.
Okay. Okay. Sorry, this is...
No problem.
All right. Okay, so then I wanted to talk a little bit next about cratered landscapes, and this is getting a little bit closer to my own research. So it's great to understand how these things form and how they work, but a major aspect of it is also understanding how terrains evolve when you accumulate craters. And the key to it is really understanding that cratering is a continuous process, which I think is very difficult for us to think about that way, because for us, impact events are a big deal. They are catastrophic a lot of the time. I mean, actually, they're not catastrophic a lot of the time, but the ones that are, you know, they really make an impression. So we don't tend to think of it as a continuous process, but over geologic time, it absolutely is. They're happening all the time, and at all size ranges. So if you look at the Moon or Mercury airless bodies, for example, they get impacts down to the microscopic scale, and then all the way up to planet-sized impacts, disruptive impacts even sometimes. But the planets that have atmospheres, like us, Mars and Venus, they actually can filter out the smallest impactors. I think that the Earth doesn't get craters that are smaller than 20 meters. I should fact check myself. And Venus, of course, has a much thicker atmosphere. It can block bigger impacts. Mars, there's actually some research going on Mars. I don't know what the conclusion of it is or what they are at the moment, but looking at the cratering record on Mars to try to see size ranges that might be missing, to see if the atmosphere could have been thicker in the past. So I have some friends that work on that, so if you're curious about them, I can point you in their direction. And then the other key is to think of it as just another geomorphological process. So cratering, shapes the surface, it erodes things, they deposit things, and just like a lot of other processes, and when they're happening at the same time as they are, on Mars, for example, these processes compete with each other at various scales to be the dominant shaping mechanism for the surface. So that's kind of the key to understanding this. And then if you saw the video that I made, this is from that, one of the fundamental uses of, crater terrains, that we can count the craters on them and compare their overall densities, and then get a sense for which surface units. You have to sort of divide the surface into units in order that you think are pretty much homogeneous to make this work, but you can get a sense for which ones might be older or younger than others. And if you just look at the moon, you can see it has two major units. You can see it with your eyes, the heavily cratered highlands and the smoother, darker maria, which are volcanic plains that are also very much covered with craters, but they haven't had as much time to accumulate as many craters total as the highlands have. So you can say that they're geologically younger. So we count up craters of each size in a given region within these diameter bins, and when we plot the number of craters against the size like that, we call it a crater size frequency distribution. And for a variety of reasons, some of them are convention, but some of them are out of convenience. We use the cumulative size frequency distribution of craters, and this typically follows a power law. So the number of craters is proportional to d to the minus alpha, where alpha is this exponent that controls how steep or shallow the distribution is. And this is just an example where alpha equals 2 to show you kind of what that looks like. So if you have one crater of size D, you would have 4 that are half that size and 16 that are a quarter that size. And when you jumble them all together, it doesn't look totally unreasonable for what you might see if you looked somewhere on the moon. It would kind of look like that. Okay, so you can plot these crater size frequency distributions for different regions together, and if you just look at the overall density, so the offset of these lines, you can tell some things about which things are younger than other things. So the highlands are older than the Maria. You can see Oriental. There's not that many other basins plotted on here, but our Oriental is sort of the youngest of the large basins, and then you can see that some of those Mare regions are younger than Oriental, which makes sense since Oriental has some of that Mare basalt in it. And the cool thing about the moon is that we actually have pieces of it that somebody went and picked up. And you can anchor those relative ages to absolute ages using rock samples, radiogenic isotopes. And this is another thing where, you know, there's a whole field that's just this. But it's super important, and actually this is resolving, or it's in the process of resolving, I hope, sort of a question or a controversy in the planetary science community about whether or not there was a thing called the late heavy bombardment, which is sort of, over time, since solar system formation, the flux of impactors has been decreasing exponentially, which kind of makes sense because we formed the planets and they're sweeping up all the available things, so the impactors that could hit things are being taken off the market. So the flux is decreasing exponentially. But there's some question over whether or not there was like one last big spike of large impacts all at the same time, and it comes from dating the basins on the moon, which seem to have occurred in a very narrow period of time altogether. But there's some doubt about whether this is actually a spike or whether this is you know, just part of that exponential trend. And if it's going to be sorted out, it's going to be sorted out by these careful teasing apart these radiogenic ages and impact glasses in the Apollo samples, and trying to figure it out from there. So that part is really cool because we can build up an entire chronology for the moon that's based on, you know, we have some places where we know this rock came from this place and we know it's that old, and we counted the craters there and it has this many craters, so we can compare that to other places on the moon and we can build up a whole system of chronology that way. And that's kind of important because we use the moon as a basis for understanding cratering records in other parts of the solar system, and we kind of scale what we expect the flux to be at the moon to what it should be at other distances from the sun to try to understand the cratering records there. Okay, so this is great. We can compare crater densities and get relative ages and things, but then we also have to understand how these things evolve. And the reason for this is because if you wait too long, if you accumulate too many craters, in some circumstances you'll come into a state where there's so many that the density is no longer reflecting the time that's passed because you've reached a state of equilibrium where enough craters are coming in that they're obliterating roughly equal numbers of old craters. So this happens in certain situations, particularly when that size frequency distribution exponent is greater than 2. And that means that there's lots of small craters compared to large craters, and this is often called the sandblasting regime. You can kind of see it's like you're spraying the surface with tiny impacts, and they kind of diffuse everything away. And in this regime, you can see that once you've reached equilibrium, which happens first at the smallest sizes of craters, and then it kind of moves to larger and larger sizes, that you lose the ability to, you can only say that a surface is so old, is older than a certain point. You can't say any more with more detail than that, unless you catch it in the middle where you have a kink in the size frequency distribution, where you're observing this very steep production function. That's the production of new craters that's in that equation. And then there's a kink where the smaller craters have reached equilibrium, and then it follows a different line. So you can still get some in-time information if you're in that situation. And this is just this is an analog experiment from 1970 in a sandbox where it's kind of an iconic one for impact cratering studies, where he observed this effect in the lab, which is very hard to do because it's very hard to get a dynamic range of craters. He used a lot of, everything, small, I think, projectiles, bullet type things, and then the bigger ones are actually formed by explosives. And you have to be random about it, and this is just so much work. These graphs, or these sandbox pictures. Anyway, you could be in the other state also, where alpha is less than 2, and that means you still have more small craters than big craters, but the ratio is a little more even. And in this case, you actually never reach that equilibrium state, because every time you accumulate a bunch of small craters, a large crater will come along and it'll erase everything, and you'll start over. But the good news there is that the slope of the size-frequency distribution that you can measure from there will tend to reflect the slope of the production function that you're putting in. And that's important because we would like to know what the production function of craters is. Again, going back to the impactor population ideas, these things can be very different or very slightly different values of the observed size-frequency distribution would give you different clues as to what are the things out there that caused these impacts to begin with. And if you look at the moon, the observed crater size-frequency distribution isn't just one power law. It has breaks in different size ranges. So it's actually really steep for small craters from a kilometer scale to, or like less than a kilometer-ish, and then it's shallower again for larger craters above that, and then for very tiny craters around 100 meters, it's shallow again as well. So this particular shape, if you could try to match that to impactor populations, and people have tried to do this, and there is, I think, a reasonable agreement with the size distribution of asteroids, then you can try to put that together to help out the people who do dynamic modeling. Like this is just one example, but this is the NICE model, which is trying to explain the evolution of planetary orbits, especially in the outer solar system, and it's sort of by modeling how the planets perturb each other over time, it is producing a potential solution or origin for this late heavy bombardment that I talked about, like some time in the solar system's past when it would have made sense that a population of impactors, in this case the in the outer solar system, a population, and did you see that? It like went crazy all of a sudden because the Kuiper belt was disturbed by this resonances between the large planets. So anyway, so that's an important constraint for models that try to do this, that try to come up with scenarios that could be responsible for creating our solar system as we know it. Okay. So I don't want to say too much about my own personal research, but what I have done most recently has to do with trying to come up with a complementary way to look at crater terrains, which is through the topography. So crater counts sort of depend on this, looking at the surface, the 2D recognition of circular features, right? And we have a really nice topography data set from the Lunar Orbiter Laser Altimeter, or LOLA, right now. It's been up there for a few years, and it's been delivering really excellent data based on laser altimetry, which you're measuring the travel time of a laser pulse to and from the surface. And there is additional information that in that topography set that is not in the crater count information. And so one of the things that I was working on most recently was trying to understand how it could contribute to understanding how crater terrains evolve in a complementary way to the crater counting way. So I'll be really brief about this. We had two approaches where we looked at the topographic power spectral density, which is pretty easily derived from the Fourier transform. It's the square of the Fourier transform. And then We could build an analytic model that sort of tracks the way that impacts accumulate over time and influence the overall power spectral density. And at the same time, we could run a numerical model using the same principles as before, where you have a certain domain, you have an imposed size-frequency distribution, and with this analytic model and the numerical model, we could try to understand how the resulting power spectral density changes this when you vary the impactor population. It's essentially the size distribution of craters that you're adding to the surface. And we would do that. We would have definitions for crater shapes. That's not very interesting, but anyway, this is just a start, and I hope that it other people will also start building on this. But we did find that we would expect that in some regions, so for example, this red dashed line is the behavior of the size-frequency distribution, and like I said, at some, if you're above 2. You can get to a state where you reach equilibrium and you can't tell anything anymore about what the original production function was. And we found that you actually can tell some more information for up till a value of 3 at least in the power spectral density. So in some ways they may actually be complementary. It's I have a paper coming out on this. It's the last chapter of my thesis. It should be coming out really soon, and I'd be happy to point you to that once it's out. But it really is just a beginning. I hope that this approach gets picked up and people build on it. So anyway, that's sort of a little bit about what I've been working on. This is something that I'm super excited about, and it should look familiar to you actually. This is from Dr. Pamela Gay's seminar on CosmoQuest, and the reason why I'm so excited about it is because finally citizen science is going to give people, or give us the opportunity to collect enough different crater counts that we can get some real statistics on the variation of them. And it was, I think, a really important result to find that having a number of volunteers count on the same surface can give you an answer that's on par with experts, because crater counting is a little bit of an art. And it's really time-consuming, and computers are really bad at it. And I tried to make the point that like very small variations in the measured slope of one of these size-frequency distributions could have big effects on what, the kinds of things that we think might be responsible for the kinds of constraints we can put on our models and things like that. So, so I think this is a really huge advancement, and I hope that it continues to draw people, because I think people power is how this is going to get improved. Okay, that's the end of the science part of my talk. I see that it's 3:50. I think I won't talk about most of the history of science thing, but I kind of wanted to just leave you with like a couple of things. So about kind of like why I think it's interesting to think about crater interpretation in the past. So here, for example, are a few different events, impact events, absolutely, but they don't leave craters. We had this spectacular fireball, I think that was just last year, in Siberia. There are meteor showers. In 1908, there was another like huge airburst impact that didn't hit the ground, is what the consensus is. I think actually the meteorite may have hit the ground, but it didn't make a crater. But it did blow out all the trees in this huge region in Siberia. And then the car, it didn't make it, a meteorite hit this car in my hometown in 1992. That's my hometown, one of my hometown's claims to fame, I guess. But it didn't make a crater either. It made that woman $50,000 for her crappy car, but it didn't make a crater. So on the one hand, you can get impact events that don't leave craters. And on the other hand, you can have all kinds of craters that aren't formed by impact. Even the ones that you think might have been in this picture. So, I mean, you can see there's a projectile experiment in the upper left. And then next to that, that's actually a World War I battlefield with bomb craters. The one next to that is a volcanic maar, so that's a volcanic feature made from a steam explosion. Then on the bottom, on the left, is Mount Vesuvius. That's a stratovolcano, and then the other picture is actually a nuclear test crater. So you can see you can make these in all different kinds of ways, and they make craters. Actually, the word crater comes from the volcanic caldera sense, not from any kind of impact sense. So this is kind of when I'm trying to think about how people would go about tackling this problem of if you have an impact crater, say you have meteor crater in your backyard, and you don't know what it is. How would you go about trying to figure out what it is? And my experience is, well, this is kind of a tricky thing, because I'll skip this, but astronomy and geology are kind of they're not the same as physics in some senses, where you can have an experiment that you set up. You have a hypothesis. It's sort of the canonical scientific method that we're taught in grade school kind of thing. Historical sciences, you have what you have, and you can't just run an experiment to figure out what it is, because you can't create another meteor crater and just watch it. And so this is kind of called the asymmetry of manipulability. How do you find ways to study the past when you can't manipulate it? And I put this picture up of a sort of iconic moment of a crucial experiment in, the theory of light, a wave or particle theory of light, where Poisson was a fan of the particle theory, and he tried to poke holes in Fresnel's version of the wave theory, and he said, well, if your wave theory is right, then it would have to produce this white spot in the middle of this circular shadow, and that's ridiculous. And they tried the experiment, and there was a white spot, and that was, sort of a way of sort of a classical way of thinking about how you do science, is through sort of prediction and experimentation like this. But that doesn't work with geology or planetary science as much. So what you have to do is find some alternative, and the way that I found that people turn to again and again is through different kinds of analogs. And the two important ones for craters are you look for terrestrial analogs, and the most prevalent choice of terrestrial analog in the past, I would say, has been volcanoes, or you try to do laboratory scale experiments. And in either case, the result, the model crater or the analog crater that you're looking at, isn't going to be perfectly representative of the lunar crater that you're trying to explain, or meteor crater that you're trying to explain. Some things will be kind of like it, some things will be really different. And you have to make choices about which things are important to care about. Like, can you just say, well, the crater on Mount Vesuvius is on a mountaintop, and meteor crater is below the surrounding surface. Is that an important difference, or is that something that you can neglect? So I don't want to go too much into this, but just try to leave you with this thought process about the actual process of doing science and the human choices that are made along the way and tried out. And this is something that really just appealed to me about the history of science when I was in grad school. That's another thing that kind of ambushed me that I wasn't really expecting. But I just am kind of fascinated with understanding. I mean, it is a very human endeavor, and collectively, we come to consensus through a very complicated process that I think is oversimplified for the sake of the public sometimes. But oversimplification is a double-edged sword, because in the end, it's all of us. It's a very human problem, and we put a human face on it. It's a different way of coming to understand the scientists behind all of the science. So anyway, so this is how I got interested in it, and you can kind of see if I skip a whole bunch to the end. Sorry. You kind of see these are some the beginnings of some papers that I was reading for my graduate science research that I started to notice. They're kind of early, but impact cratering is one of those fields where you still cite papers from 40-ish years ago because they're still relevant. somehow, which is kind of weird, but it's true. And if you read them carefully, like they're actually kind of hedging about whether impact craters are impact features or not, because at that time in the 60s, and even as well, mostly just the 60s, it's still not 100% clear, and that was kind of a wake-up call for me, because I grew up quite some time after the moonwalks and everything, and there was nobody ever mentioned any sliver of doubt that the craters on the moon were impact craters. There was just like a fact that I knew to be true. So it was kind of neat to come across references to people who, you're not sure, and it's just an interesting problem to me. What do you do when you're not sure? So anyway, that's sort of an introduction to how I got interested in that. I could talk about that for a long time, but I won't, because it's already 4 o'clock. And I think if there's any questions, maybe I'll flip off this screen share finally. So hello. And I don't know if you have any questions for me, or places where I could point you to more information or anything.
Okay. Let me make a quick announcement to those watching online. You can either use the hashtag GHO seminars, and we'll pay attention to that and see any questions if you're watching on YouTube. Also, if you're watching the Google Plus seminar stream, there's the Q&A feature, so we are going to be looking at that as well. But we'll start off with any questions in the audience.
All right, I've got one here. What you got? I have one. When discussing the crater size density frequency, there seem to be problems if alpha went much above 2 or below 2. Is there a tendency for alpha to end up in the 2 range so you don't get obliteration?
So I had a little trouble, but your question was, is there a tendency for alpha to end up in the range around 2?
Yes, yes.
I don't think that that's a natural point. I don't think there is any natural point that it would fall upon. It happens that the population of larger craters on the moon, and especially in the heavily cratered highlands, alpha is about 1.8. Whether that's a coincidence that it's so close to 2, it's a little bit speculative. But because if you do reach, I think I understand your question. If you do reach equilibrium, if you had an impactor population with alpha that was very high, and you waited long enough until all size ranges came into equilibrium, the resulting slope would be 2.
And the reason I ask is it's somewhat similar to the rank size rule in urban geography. You can, if you know the size in an ideal plane without with transportation options in every direction, and without looking at specialized cities, if you know the population of your largest city, you can pretty accurately predict your 2nd, 3rd, 4th, 5th going down. And it looked somewhat similar to the ratio of large impactors versus medium versus small. It's kind of interesting that, and here I'm dealing with human beings, which are about as erratic as shit.
Yeah, it is kind of interesting. If alpha is exactly 2, then every crater size is occupying an equal area of the surface, and at that point, that means that there's no special scale on the surface. And there's if you didn't have other indicators like tectonic features or a lunar lander in the frame or something like that, it would be kind of hard to tell what scale you were actually looking at.
Okay. There's a question online there with the Google Q&A. I'm going to go ahead and select that one. Let's see.
Okay. I can answer that.
You want to read it out loud for those who are watching?
Are there equivalent numbers of impact craters on the near and far side of the moon? And since the near side always faces the Earth, is it partially shielded from as many impacts? So it's a trick question, because the near side of the moon has a lot more of those Maria deposits, which happen to be geologically younger. So in that sense, they haven't accumulated as many impacts total as the highlands have. And the far side of the moon which is not the dark side. It's like a phrase that really gets on my nerves. The far side of the moon is completely covered in highlands for the most part. There's almost no deposits of the Mare material. So I guess there are more craters on the far side of the moon than the near side of the moon, but it's not because of any kind of shielding effect at all. The cratered, the distribution of impact angles is pretty much random. There are people who are researching whether there's a very slight advantage to being on the leading or trailing side of the moon in its orbit. I don't think the results of that are conclusive, but there's a kind of a statistics of small numbers thing going on with that. I know there's a paper that has to do with the large basins, and maybe there was a slight preference to be on the leading or trailing side of the moon, not near or far, but the opposite. But yeah, it's kind of a statistics of small numbers problem.
Okay.
But the moon also doesn't act as a shield for the Earth, just unfortunately.
Now, when you see it, you get a feel of that it's a lot closer, and I guess it really is. Your cross section of getting hit is for the moon is still pretty large, even for that piece that's looking towards us. The Earth is so far away from it that it's still a pretty good target, right?
Yeah. Oh, yeah. I think I saw the other day, and I think it's true that you could actually fit all of the planets end to end between us and the moon. So it's close, but it's not that close. It's still there's still quite a distance.
Okay, pretty cool. All right, any other questions? All right.
I wrote down a few questions after going through. A couple were just about like your PhD movie.
Yeah.
Is that like on DVD? Is that a DVD?
It is on DVD. It's also streamable. It's at, let's see, you get it right, phdcomics.com/movie should get you there. They actually just filmed a second one that I didn't produce that one, so I'm a little bit out of the loop with it, but I know they just finished filming, so that should be coming up in the near future too.
Comedy?
The first one, yeah.
Documentary? What is it?
Sorry, say that again?
Is it like a documentary or a comedy, or what is it?
It's a comedy. It's a comedy with heart. I think that's the official line. But it's about grad school. It's about academia.
Gotcha.
I don't know if you've ever heard of the webcomic, but it's sort of chronicles the trials and tribulations of being in. I mean, grad school is kind of just this really bizarre world where you work all the time and feel really guilty about things, but you also make progress and have successes, and it's kind of a long haul for a lot of people. It was for me, and the comics are a little bit darkly humorous. But check out the comics. If you like the comics, you'll definitely like the movie.
Okay, gotcha. Well, a more serious question was,
okay.
You discussed how some of the larger impacts could have an effect on the tilt of the axis of some of the planets in our solar system. Do you think that, like, how large of an impact would it take to actually change the Earth's axis tilt? And yeah, have there been any that there are theorized to change the Earth's axis tilt?
I don't think so. But I mean, let's see. If you look at, and I wish I had been more prepared with like YouTube videos or something, but if you look at the simulations for the formation of the moon, for example, there's also giant impact scenarios for Mars. The southern hemisphere of Mars is very different from the northern hemisphere, and it's possible that that could have been created by a really large oblique impact, so one that didn't hit straight on but had a very glancing blow. And I think that's the kind of impact that's more likely to affect things like rotation. And there's it's not really clear how many of these giant impact scenarios are going to turn out to be what actually happened in every case. But there's kind of a general thought that, you know, as the final stages of the secretion process are going on, multiple protoplanetesimals sort of formed, and then they're all interacting with each other. So possibly the last few impacts, which are the biggest ones, are going to be, you know, causing these stochastic, you know, like slightly random, how it turns out, if you ran the solar system model 100 times, you might get something different every time. So it's kind of hard to take our one case and figure out what happened in that sense. So that's what the people with the dynamical models are trying to do. They get to run solar system formation thousands of times.
Gotcha.
Okay. So I've got a question. Could you give us a little background? You talked a little bit about your experiences in graduate school and how you got to learn about a lot of different things that then sort of stretched you out into looking at history of science and the history of craters in addition to the science of how they form. Could you kind of explain to these undergraduates who are looking at potentially going to graduate school what that experience is like and sort of what your trajectory had been in going through grad school and where you're at now?
Sure. Okay, I can say, so I went into undergrad convinced that I was going to be a physics major, which I was kind of, but it wasn't until I got there that I found out that there was such a thing as sort of combining physics and geology, geophysics. And I didn't know that was a thing before I got to undergrad, and I got very interested in that because I think that's what draws me to planetary science to begin with, the idea that you can learn a lot about what's going on a planetary scale, sort of using you know, pretty basic principles of physics. You know, like there's the things that really interest me, like the Grail mission that I was talking about that can map the gravity fields and then tell you about the interior mass distribution of the moon, which can tell you about the state of the core. Is it solid or liquid, or how big is it, or you know, what's going on in places that we can't access otherwise. Those things really appealed to me, and I just didn't know that that was a thing that existed. But that's why I went into planetary science, and I decided to go to grad school, partly because there's no industry for planetary science, so academia is a pretty common pathway for people who major in that. Maybe there will be soon, SpaceX, I don't know, but there isn't one right now so much. But yeah, and then once I got there, it's kind of like the same thing happened. Like I didn't know that history of science was something that I would be interested in. I think because the way that history is incorporated in science curricula is like sort of, you know, the way it was for me was like there's people really like anecdotes, and they would tell an anecdote to introduce a topic before moving on to the actual science of it. So I kind of got this idea that it would be boring, the history of science. It would be like a list of names and dates and whatnot. And what I found when I got started with it was that it's the way, even the way that we've thought about the history of science has changed over time. Like we used to think about it differently than we do now, and there are differences between the different sciences and how they're done. So like I was trying to describe, you know, with the crucial experiment versus the historical sciences, people have different strategies for finding out information, and there is no one scientific method. I think like that's what really got me interested in that, because it's kind of just a thing that everybody was telling me in my science classes all the time, that you have to follow the scientific method, and you do this and then you do that. And as a graduate student, you kind of find out very quickly that you're doing lots of things, and they're not all following that scientific method. There are multiple scientific methods, and a lot of what you're doing is learning from other people and learning a lot of hands-on things that are not in any textbook, and you're learning from older grad students about how to make the code work and how to troubleshoot, and it was kind of, I think the two kind of clicked for me, like the learning how to do science research in a grad school setting, and then also coming across this entire field where people study exactly that. And I think it kind of was appealing to me too, because to have this idea that, you know, there's people who love science just as much as people who do science, and they love it so much that they try to go back and understand past iterations of ideas. Like that sounds hard to me, and it sounds really challenging and fun. Like, it's hard enough to understand the concepts, at the cutting edge now, but then to try to say, to understand all of the previous understandings of the same topic, like, it just seems extra hard and kind of neat and fun. Did I answer your question?
Yes, you did, and it gives me an opportunity to jump off and mention one of the great books I read it last year. It's Westfall's biography of Newton, called Never at Rest, and I really enjoyed that one. Probably a lot of really good biographies of Newton, but what impressed me with that book was how the historians of science, especially you're looking at a historical figure like that, go back to try to understand, well, how did Newton do calculus?
Mm-hmm.
And if you think calculus is hard now, you have no idea how he made it to be so impossibly difficult to understand. But it's amazing. That story is absolutely amazing to get the background for what was Newton's thought process in developing the calculus, and then everything else the guy did. I mean, he was
yeah. I see another question.
Read it off and answer it.
Okay, so what are your thoughts about using new media outlets such as YouTube, Vimeo, Tumblr, Twitter, etc. to communicate the latest scientific discoveries to the general public? I'm all for it, as I don't know if you can tell, but yeah, so partly the kinds of things that I do as a science communicator, which is kind of a funny term, is I make YouTube videos like the one I made about the impact things, and then the ones I made a few for JPL missions, just to kind of explain topics using visual and audio together, which is, I think YouTube is a really great space for science right now, and it's got a lot of really creative people that are doing things, doing things regularly, all the time. Every week they're posting a new video, and it's about really cool things. And it's just a lot of effort too, so it's kind of neat to see it come up to this production value standards. Anyway, so video-wise, I think video is an excellent way to communicate. Also, Twitter, I really like Twitter. I think it's sort of kind of fun to meet people. I've met people I would never be able to meet otherwise and talk to them. You can easily reach out to people on Twitter, and they don't have to answer, but it's just it's kind of an equalizing medium, kind of, in that sense, and I really enjoy that. I've also participated in a couple of rotation curation accounts, so I curated Real Scientists is one of them last summer, where every week they get a different scientist to tweet for a week and sort of basically about the kind of science that they do and what they do on a daily basis. And that kind of thing, I think, is really important, because it's getting to people who are practicing scientists, or like me, or who are recovering scientists or science communicators, about what it is that they do on a daily basis. And I think there's just nothing more important than putting a human face on what scientists do. So this is one way that's into that. We're like, well, I like science, I like pretty pictures of data just as much as the next person, but what do you do on a day-to-day basis? And I think that's really important. I've also done one for the humanities. It's called We the Humanities, and I really enjoyed that one also. So yeah, transparency. I think humans do science is like the thing that I most would want to get the world to understand. So,
yeah, I used to, 2 years ago, I attended a workshop from NSF. It was a science communication, becoming the messenger endeavor on their part to get NSF-funded people or research scientists in general to try to communicate more on the new media platforms like Twitter. And I at first poo-pooed the whole idea. I thought, oh my God, there's no reason why I'm going to be on Twitter. It's ridiculous. And it was within a few days of being on Twitter that I realized, oh my God, there is so much out here that is just amazing and cool, and you could spend years of your life just digging down and reading and learning about all the things that people talk about. It to me has been remarkable. It's really
Yeah.
good.
Yeah, me too. It's also really useful for conferences, especially if you can't go to one. But other people are going to the conference. You can follow along with what they are learning using hashtags and whatever. And I found that to be really helpful. Just because, you know, sometimes you can't go and you still want to find out the big highlights from the press conference about what's happening on Mars and whatever. And Twitter takes care of you that way.
Do we have any more questions here? I've got one more. So, what advice would you give young undergraduate students?
Okay. Just in general?
Whatever you want to tell them.
Okay, well, from the stories from my own background that I told you, I think, well, you could predict that I'd say as much as possible, find out what the different options are, because I never would have predicted that my path would have gone the way that it did, and it's like completely because I came across different these fields that I just didn't know about at the time. So as much as possible, I know it's probably sounds silly, but like I read the course catalog, and that's how I found out that Caltech has a minor in the history and philosophy of science. And I went to a class, and I expected it to be boring, and then it wasn't boring, and now it's like one of the most excited. That's one of the things I'm most excited about. So you just you can't really predict which events like that. So I just my most heartfelt advice is to keep your ears and eyes open, and don't try don't blow it off if you think you might be interested in something, because it could become what you do. You never know.
All right. So we got anything else you want to ask? Well, we want to thank our speaker for this fantastic seminar.
Thank you very much for having me, and I hope that was entertaining or very interesting. And again, if you want to get in touch with me, Twitter is probably the best way. I'm at True Anomalies, which is a celestial mechanics term, if anyone's wondering. But I'd be happy to follow up on anything if you were interested in some of those subfields that I glossed over really quickly, or anything like that. Yeah, I'd be happy to follow up.
Okay. Well, it was a too short of an amount of time, and I wish we could have had you come back and do 3 more. That way we could get the whole shebang. But we appreciate your time, and thank you very much. And we look forward to hopefully hearing from you again.
Thanks so much. This was fun.
Okay. All right, we're going to stop the broadcast right now, but we'll chat for just a bit more.
Okay.